All right, now that we should be pretty familiar with operating with fractions at this point. Okay, we can multiply, we can divide, we can add and subtract fractions. Again, the difference between those two, multiplication and division, do not require common denominators. Addition and subtraction of fractions do require common denominators. So solving equations with fractions really is no different. We just have to determine which operation we need. Let's talk about solutions, right? So just real quick, remember, a solution is a value that we can replace a variable with in an equation to make it a true statement. So yeah, solve for x, or when it says solve, it really is asking you what value of x makes the equation a true statement. So the principles of equality, this is where the determination of what operation we're using with the fractions is important, because remember, whatever you do to one, this principles of equality is just saying whatever you do to one side, you got to do to the other side. All right. So yeah, and this slide should look familiar because we've seen it before. And usually we're solving for x, but we're just manipulating these to be what we want, which is, of course, x equals or whatever the variable is. But again, I can't emphasize this enough. Whatever you do to one side of the equal sign, you must do to the other side, whether it's division, multiplication, subtraction, or addition. So remember, this is just a nice quick review using principles of equality. This one has no fractions. So x minus 4 equals 7. What value of x would make this true? And yeah, you may not even need the principles of equality, but I'm going to demonstrate it just so we can remember, all right? So I have x minus 4. What I really want would be x equals something. I don't want x minus 4 equals something. I just want x. So how do I get rid of that minus 4? Well, if I change it to a 0, then I can ignore it. And the way I do that, as you can see, is I just add 4 there to make it 0. But if I just leave it at that, then I've changed the whole equation. Because the principle of equality says if I add 4 to the left side of the equal sign, I should also add it to the right side of the equal sign as well. So 7 plus 4 is 11. And again, you could check, right? 11 minus 4, what does it equal? Yes, it does equal 7. So that would work out, right? We check that off. So 11 would make that original equation true. So the same principles of equality are going to apply with the fractions. It's just now we're operating with fractions. So in an example like this one, again, the idea is to get x equals something, right? Instead of x minus or multiplied by something, I just want x. So I don't want that minus 4/3 there. So how do I get rid of a 4/3? A negative 4/3, really. I'll just add it. Because negative 4/3 plus 4/3 is 0, which is what we want. But again, if I do it to one side, I must do it to the other side. In fact, I'll even write it like this, horizontally, so we can see the addition more like we're used to with fractions. So 7/3 plus 4/3, we already got common denominators in thirds, so just do 7 plus 4, which is 11. 11/3, right? Now that seems pretty good. But what I would want to do in my calculator is just check, but instead of using x, I'm going to use 11/3. So 11/3 in my calculator minus 4/3. What do we get? Minus 4/3, 7/3. So that checks off the answer. It confirms that x being 11/3 makes that a true statement. So what about a problem like this one? You guys try this one out. Take about 30 seconds and see if you can solve for x on this one, or what value of x would make this a true statement. All right, 30 seconds, go. So since this can be done in one operation, It's really just a one-step equation. Just to compare this one, if this was showing as 3x equals -9, I mean, what would you do in that case? Well, you'd divide both sides by 3, and then you'd have what really is 1x, right? But we usually just show that as a phantom one. So that'd be x equals -3. Now, again, this is just kind of an additional example to compare with this one, right? So, since I divided both sides by 3, what I can do in this case is simply to divide both sides by 3/8, right? So I'm still using principle of equality for division. But anything divided by itself is 1, which would make that 1x, which is what we want. But the principle of equality, of course, means that if I do it to one side, I do need to do it to the other side as well. So divide that by 3/8. But again, we don't actually divide with fractions. We end up multiplying. So it's -9/10. But now it's multiplied by the reciprocal, which is 8/3. So again, you could cross simplify at this point, right? 9 and 3, that's going to be now 3 and 1, because they're both divisible by 3. And then even the 8 and 10, right? The 8 and 10 are both divisible by 2, which is going to make that 4 and 5. So now I'm ready to multiply. Let's see, okay. So 3 times 4 is 12, and 5 times 1 is 5 in the denominator. Don't forget that that 9/10 was negative, so this is going to be a -12/5. It equals that. Now this one just said to solve, so even though we could change this into a mixed number, which would be, well, -2 and 2/5. Again, it shouldn't matter which one you type into the homework, because they're equivalent in value, and one isn't necessarily more simplified than the other, okay? But again, I do want to check just to confirm that x being -12/5 would make the original equation a true statement. So when I type this into the calculator, 3/8, and I'm going to multiply it, because it's 3/8 times x, I'm going to multiply this by -12/5. And what do we get? -9/10, which is what we had in the beginning. So it shows that x being -12/5 makes the original equation a true statement. So either one of these would work. So same idea on this one. It's just that it's negative now, right? So instead of dividing by 5/8, I need to divide both sides by -5/8. So I'm going to take the -5/8 and we'll divide it by -5/8. Now, I just showed the division in two different ways, right? In the last problem, I actually showed it by divide, and it doesn't really matter which way you do it. Just remember, whatever you do to one side, you got to do it to the other side as well, okay? So that's a 1b now, and that's, well, 13 divided by -5/8. I would just change that to 13 times -8/5 now. That's 13 over 1, so 13 times 8, let's see, 104, it's going to be negative. 104 over 1 times 5, which is 5. So again, I would just leave it like that, but if you want the mixed number, that's okay. It's a -20 and 4/5. So again, let's just double check in the calculator to make sure this works by replacing the b with -104 over 5. So the calculator confirms that b equals -104/5 makes this a true statement where it equals 13 right there. All right, take 1 minute and see if you can solve for y on this one. Again, what value of y would make this equation a true statement? All right, 1 minute, go. All right, hopefully that was enough time. If you're still finishing, just finish up. But just to kind of speed up this process, because we've already seen how to operate with fractions, right? I'm going to be using the calculator to perform the operations, all right? All right, so the first thing I would do on this one, right, it's like a two-step equation, is I need to get rid of that plus 1/5, so I just have at least the negative 1/4 y by itself. Or to say it's isolated. That's what some other people would say, all right? So I need to zero out that plus 1/5 by subtracting it from itself, right? So 1/5 minus 1/5 is 0. That zeroes out. But I need to do it on the other side as well. So I have negative 5 minus 1/5 as well. All right, so let's put that in the calculator. And it looks like it gives me negative 26 fifths right there. Now this should equal what we had remaining, which was the y stuff. Negative 1/4 y equals negative 26 fifths. Well, at this point, I would say, well, I'm going to divide both sides by negative 1/4. Why? Because anything divided by itself is 1, and what we really want is 1y. So if I do it to one side, though, again, I must do it to the other side. Negative 26 fifths divided by negative 1/4. And again, I'm going to put that in the calculator to see what it is. So the calculator gave us positive 104 fifths. But since we use the calculator, we didn't really show a lot of work on that. I mean, we've shown plenty of work for this problem if we're doing it on a paper test. But I'm just going to use the calculator to confirm that 104 over 5 makes that a true statement. So yeah, the calculator shows that it equals negative 5. That is a true statement because it showed that it was originally equal to 5, negative 5. So again, I feel a lot more comfortable circling it, boxing it in, putting it in the homework, whatever the case may be. All right, a problem like this one, it may sometimes cause some problems, but if I were to rewrite this so it looks a little bit more familiar, you could do the same as well because we're just applying properties of fractions, really. So if you prefer to see it as 3/7 x there in the beginning, you could. Right, then a plus 7 equals negative 7. It's not really going to change. It does not change the value of that 3x over 7, all right? Just depends on where you prefer to see the x. So from here, everything just works the same, right? We need to get rid of that plus 7, so minus 7 from both sides. Makes that negative 14. This zeroes out. And then I would have 3x over 7. That's fine. Now, if you see it as 3x over 7, a lot of students that prefer to see it this way, they do it in 2 steps instead of 1. Here's what I mean by that. So they first get rid of the denominator by multiplying both sides by 7, right? Because 7 divided by 7, or that these would cross-simplify into a 1, okay? So that would then be 3x equals negative 98. I think I did that right. Yeah, that should be good. Then divide both sides by 3, and then x equals negative 98 thirds. So whichever way you prefer to do it, doesn't matter. You should get the same answer, but let's just check in the calculator to make sure that negative 98 thirds as x makes the original equation a true statement. So the calculator shows when I replace x with negative 98 thirds, that it still equals negative 7. That is a true statement. All right, so with that in mind, try this one again. Again, it's very similar to those last two, but try it out. Take 1 minute, and then we'll go over it. All right, here we go on this one. So again, the first thing I'd want to do is get rid of that 1/8 or zero it out. So it is positive 1/8, so if I subtract 1/8, that zeroes it out, right? So minus 1/8 over here as well. I'll just use the calculator to do that work. So yeah, that gave me 7/24. So my equation now, after zeroing out that plus 1/8, I got 5/4 x equals 7/24. And then we'll divide both sides by this 5/4 stuff. And again, that's going to make that 1x. And I'll put the 7/24 divided by 5/4 in the calculator. So 1x equals 7/30. So I'm going to replace that with x, right, in the original equation, and just make sure that it gives us a true statement. And it gives us 5/12, which is a true statement. So again, I feel pretty comfortable about saying x equals 7/30 is the solution for this equation. So for isolating the variable, let's go back into module 2, right? Where if we had an equation like this one, 2x plus 9 equals, I mean, it doesn't even matter. Let's say 25, all right? Something like this. So we say isolate the variable. That means that I don't want anything added or subtracted with the x's. Now, I'm only looking on the left side of the equal sign in this case because that's the only place that I have the x's. Right now, this is not with fractions, but the same thing would apply with fractions. So that plus 9, I just can't have it there, which means that I need to zero it out. So isolate the variables you could also interpret as zero out any values being added or subtracted to the x's. So how do I zero out a plus 9? Just subtract it. Just remember the principle of equality still applies. So if you subtract 9 on one side, you still have to subtract 9 on the other side as well. So that zeroes that part out. And now I've isolated the x's as 2x, which equals now, what is that, 16? So let's write one with fractions. Let's say it was like 2/3 x plus, I'm trying to use similar values here just to kind of show that it still works with these, right? So 9, let's say 9, I don't know, 9/5 equals 25, and this one, again, it doesn't matter. Well, let's use, well, fourths, okay? So just like in the example above, how we got rid of the 9, in this case, the 2/3 x is adding the 9/5. So to isolate that x right there, the 2/3 x, I need to zero out the 9/5. Well, that's a positive 9/5. So to zero it out, I need to subtract 9/5, right? Because 9/5 minus 9/5 would be 0. But in doing that, I've also forced the principle of equality to show up, where if whatever I do to one side of the equal sign, I must do it to the other side as well. Now this would drop the 2/3 x, and this would equal, I mean, whatever 25/4 minus 9/5 is. And I can just put that in the calculator. So there's 89/20. 2/3 x equals 89/20. Now this has isolated the variable. The last thing that we would want to do is to make the coefficient of x. Now that goes back a ways into module 2. But the coefficient of x is the number being multiplied by the x. So in this case, it's 2/3 in the fraction problem, the second example. So whatever the coefficient of x is, I pretty much just divide it on both sides. So if that's 2/3, what I really want the coefficient of x to be is 1, right? So 2/3, how do I make a 2/3 a 1? Well, I need to divide it by itself. Anything divided by itself is 1. That's the fastest way I know to make any value 1. So I got divide by 2/3, and I have to do it to both sides of the equal sign. So I also need to divide the 89/20 by 2/3 as well, which I can just do that in the calculator, right? So divide that by 2/3, and I get this 267/40. All right, now for the example above, though, the 2x equals 16, the same concept applies. The coefficient in green there is 2, How do I make a 2 of 1? Well, you just divide it by 2. But again, if you do it to one side, you got to do it to both sides, which would then make that 1x equals 8. All right, so that's, I went a step further. It's not just isolating the variable. That also would be continuing on to solve the problem. And of course, the last thing you'd want to do is check. So I used a calculator for this one, but if I didn't, let's go back. 89/20ths. And this was divided by 2/3. So yeah, you keep that first fraction the same, the dividend 89/20ths. Change the division to multiplication and reciprocate that fraction into 3 halves. And you can see from that, right, from the fraction multiplication here, 89 times 3 is 267. And then 20 times 2 is 40, which is the same answer we got on the calculator. So, I recommend using a calculator because it allows us to do those operations pretty quickly. But yeah, if you're doing it by hand, this is what you would do. Is if you looked at this as a, let's show that part, that 2/3 x equals 89/20ths. So if you saw something like this, you can do it in 2 steps. I like to show it in 1 just because it's quick and it's consistent with what we've been doing before with just dividing by the coefficient. However, if you looked at this and still applied the principles of equality, right? So it's like, well, look, I'm going to multiply both sides by 3 in this case to cancel out the denominator, which would then make 2x equals 267/20ths, right? That still works. And then, like you said, to divide by 2 there, right, which is really 2/1. And then I end up with 267/20ths. But I change that to multiply by 1/2. I still get the same answer there as 267/40ths. So, yeah, the method is still valid. It's just, I would say it adds an extra step, but to say it's more difficult, no, it's not more difficult. Is it more complicated? No. Is it incorrect? And that's the main question we want to ask is it incorrect? No, it's still correct. It's still a valid method to use. So if you're like, yeah, I'm going to do this in 2 steps, and that's the way you understand it, yeah, feel free to do it that way.